SpaceX's Starship Flight 11 represents a pivotal moment in the evolution of reusable rocketry, showcasing a series of technical advancements that push the boundaries of what's possible in space travel. At the heart of this flight's success was the Super Heavy booster's landing sequence, which incorporated novel engine configurations designed to enhance control, redundancy, and overall reliability. Unlike previous iterations, where the booster transitioned from 13 engines to just 3 during descent, Flight 11 introduced an intermediate 5-engine phase. This involved maintaining the central 3 Raptors while activating 2 additional ones from the middle ring, positioned symmetrically on either side. The rationale behind this setup is multifaceted. Primarily, it allows for finer-tuned thrust modulation, enabling the booster to adjust its trajectory with greater precision as it plummets through the atmosphere. Moreover, this configuration builds in redundancy. If one engine fails, the remaining 4 can compensate, preventing catastrophic loss of control. This isn't an entirely new concept. Echoes of it appeared in Flight 10, where SpaceX deliberately shut down a center engine mid-burn and switched to a backup from the middle ring. However, Flight 11 refined this approach, gathering critical data for the upcoming V3 booster versions, which are slated to standardize 5-engine descents. The footage released by SpaceX, particularly the close-up views of the landing burn, underscores the engineering prowess involved. Igniting all 13 Raptors at just 2 kilometers above the ocean's surface generates immense deceleration forces, slamming the brakes on a vehicle still hurtling at supersonic speeds. The hypersonic grid fins, 4 in total, play a crucial role earlier in the descent, steering the booster toward the landing zone as it slices through denser atmospheric layers. While the new clip doesn't capture this phase in detail, cross-referencing with the full live stream reveals the booster's velocity dropping from over 1,400 kilometers per hour at 4.5 kilometers altitude in the seconds before ignition. This seamless integration of aerodynamic control with raw propulsion power highlights SpaceX's iterative design philosophy. Each flight builds on the last, turning potential failures into stepping stones. The hovering maneuver that followed the throttle down to 3 engines is particularly noteworthy. For approximately 6 seconds, the booster maintained a stable hover, demonstrating exceptional attitude control. This capability is essential for the ultimate goal of tower catches, where the booster must align precisely with the launch tower's mechanical arms, affectionately dubbed chopsticks by enthusiasts. Achieving such stability without immediate splashdown or explosion marks a significant leap forward, proving that Super Heavy can loiter in position, adjusting for winds or minor deviations. Beyond the booster, the upper stage, Starship itself, executed maneuvers that simulate real-world return scenarios, adding another layer of innovation. One standout feature was the dynamic banking during the subsonic phase of re-entry. This test mimicked the path Starship would take when returning to Starbase in Boca Chica, Texas, steering from a re-entry corridor over Mexico to a precise landing orientation. The guidance system had to ensure not only directional accuracy, but also proper vehicle alignment for capture by the tower arms. This isn't trivial. It involves navigating a narrow flight corridor to minimize risks to populated areas, as outlined in SpaceX's FAA proposal. The proposed trajectories, either a southern path between Yucatan and Cuba or a northern one via Florida, prioritize over-water flight to reduce ground hazards, with the FAA mandating harm probabilities below 1 in 10,000 per mission. By successfully demonstrating this banking, Flight 11 validates the subsonic control algorithms, paving the way for routine site returns. Additionally, the belly flop descent, captured dramatically by drone footage from 4 kilometers above the Indian Ocean, showed remarkable stability. The forward and aft flaps remained largely intact, a clear improvement over Flight 10's damaged counterparts, allowing for controlled drag and minimal wobbling before the 3 sea-level Raptors ignited for the flip-to-vertical maneuver. These technical feats are amplified by SpaceX's broader strategy of data maximization. Even though this was the final outing for this booster iteration, the company squeezed every ounce of utility from it, conducting aggressive tests like the more angled return in an earlier attempt that ended in explosion. Failures, as the content notes, are invaluable, refining parameters for Flight 12 and beyond. Elon Musk's confidence in the system shines through, with plans for full tower catches of the upper stage targeted for spring 2026. This timeline, while ambitious, aligns with Starship's core ethos: rapid reusability, akin to aircraft turnaround. In-house innovations, such as the automated tile production facility in Florida, churning out up to 7,000 heat shield tiles daily, support this vision, ensuring scalability for frequent launches. Overall, Flight 11's highlights illustrate SpaceX's relentless pursuit of efficiency, turning a successful test without explosion into a treasure trove of engineering insights that propel humanity closer to multi-planetary status. While Starship Flight 11 demonstrated impressive technical strides, it also spotlighted ongoing challenges with the vehicle's heat shield, a critical component for achieving true reusability. The heat shield, composed of thousands of hexagonal tiles made from advanced ceramic materials, is designed to protect the stainless steel structure from the extreme temperatures of atmospheric re-entry, which can exceed 3,000 degrees Fahrenheit. However, footage from the flight revealed significant damage, including shredded areas around the aero cover, burn-through marks on the body, and a large tear between the middle and upper sections of the ship. These issues were exacerbated during the transonic and subsonic descent phases, where tiles and debris were seen flying off. SpaceX's decision to intentionally remove several tiles before launch, some in groups of 4, and others without their usual pins and backing layers, exposed bare stainless steel to plasma flows, deliberately stressing the system to its limits. This approach, while valuable for data collection, underscores a core controversy. Is Starship's heat shield truly progressing toward rapid reusability? Or are these tests masking persistent vulnerabilities? One of the primary technical hurdles is plasma wicking, where superheated plasma infiltrates gaps between tiles, degrading the boron oxide within and causing structural failure. Even with innovations like the crunch wrap, an insulation blanket using Vulcan felt to seal edges and prevent plasma intrusion, the shield showed dynamic failures. Post-re-entry images displayed long white streaks of burned residue, a mix of spalled Pica X material and oxidized boron, indicating that heat was bleeding through despite the upgrades. Elon Musk acknowledged that while the shield on Flight 11 performed better than on Flight 10, full reusability remains elusive. The tiles, produced in a high-tech Florida facility at a rate aiming for 7,000 per day, require about 40 hours from raw materials to completion. But refurbishment times could still mirror the space shuttle's lengthy downtimes if issues persist. Critics argue that pushing the envelope with intentional exposures risks overconfidence. For instance, a heavily damaged flap in prior flights caused the vehicle to drift off course by dozens of kilometers, which, while not catastrophic, highlights fragility in a system meant for routine Mars missions. Transparency, or the lack thereof, fuels much of the controversy surrounding these challenges. SpaceX's released footage consistently cuts off just before splashdown explosions, as seen in both the booster and upper stage clips from Flight 11. This practice contrasts sharply with earlier transparency, such as montages of Falcon 9 and Grasshopper failures, which built public trust through candid sharing of setbacks. Detractors, including aerospace analysts, suggest this selective editing downplays failures, potentially misleading stakeholders about the program's maturity. In a field where safety is paramount, especially for crewed missions, such opacity could erode confidence among regulators, like the FAA, who already scrutinize Starship's environmental and public safety impacts. Moreover, the aggressive testing regime raises ethical questions about resource allocation, with each flight costing millions. Intentionally inducing failures to see how much Starship can take might accelerate learning, but also delays milestones. Proponents counter that this Darwinian approach, exposing weaknesses early, has proven effective, as evidenced by the vehicle's resilience. Even with missing tiles, Starship completed its maneuvers without disintegrating. Broader debates tie into reusability's feasibility on the scale Musk envisions. Starship aims for aircraft-like turnaround, launching multiple times daily without months-long overhauls. But current heat shield limitations suggest that's years away. The in-house vertical integration from material sourcing to tile application is innovative, demanding precision down to a 1 mm edge radius to minimize failure risks. Yet, molecular-level challenges like tile shape-shifting during curing persist, leading to gaps that plasma exploits. Some industry voices, including former NASA Administrator Bill Nelson, imply that rushing reusability for Mars might overlook lunar lessons, where similar heat management is needed for landers. Tom Mueller's Impulse Space, with its moon-focused architecture, avoiding in-space refueling complexities, presents a contrasting model of incremental progress, potentially highlighting Starship's high-risk strategy as controversial. Ultimately, while Flight 11's heat shield data advances the quest for a fully, rapidly reusable system, it also amplifies skepticism. Can SpaceX solve a problem no one has fully cracked before? Or will these controversies slow the path to interplanetary travel? In the high-stakes arena of space exploration, Starship Flight 11 has ignited a firestorm of strategic debates, pitting Elon Musk's audacious Mars-first vision against calls for a more measured, moon-centric approach, all while racing against ambitious timelines that could redefine humanity's cosmic destiny or lead to spectacular setbacks. Musk, the unyielding architect of SpaceX, doubles down on his dream of Mars colonization, painting a vivid picture of ferrying over 100,000 souls and a staggering 1 million tons of cargo to the Red Planet. His words echo with urgency. This isn't just about planting flags. It's about forging a self-sustaining bastion for human consciousness, a lifeline against earthly catastrophes. The critical threshold, Musk declares, is making Mars thrive, even if Earth's supply ships vanish. This bold narrative, amplified by SpaceX's recent website revamp, targeting lunar pit stops in 2028 and Martian leaps by 2030. With payloads priced at a tantalizing $100 million per metric ton, fuels excitement, but it also courts fierce controversy. Critics whisper that Musk's obsession risks hurtling humanity into the void unprepared, bypassing the moon's invaluable lessons like a gambler skipping the tutorial. Enter the moon advocates, led by heavyweights like former NASA Administrator Bill Nelson, who thunders, "You can't conquer Mars without mastering the moon." Nelson's stance is a clarion call. The Artemis program's early phases aren't distractions. They're the crucible where scientists forge the knowledge needed for Martian survival. Imagine it. Lunar landers battling regolith and radiation, teaching us to build habitats, extract water ice, and perfect propulsion in a harsh vacuum. Musk can't land on Mars without a proven lander, Nelson warns, framing SpaceX's NASA lunar contract as no mere side quest, but the epic prelude to the main event. What he learns on the moon, taming descent thrusters, shielding against micrometeorites, could spell the difference between triumph and tragedy on Mars's unforgiving dunes. This tension escalates with Tom Mueller, SpaceX's legendary first employee and propulsion wizard behind the Merlin and Draco engines, now charting his own course with Impulse Space. Having bolted from SpaceX in 2021, Mueller's venture is a moon-focused rebellion, delivering in-space propulsion that sidesteps the refueling nightmares plaguing grander designs. Mueller's blueprint is a thriller in itself, the Helios kickstage, a powerhouse with high delta-V, whisks a custom lunar lander capable of hauling 3 tons of cargo from low Earth orbit to the moon's surface in just a week. No pit stops required. Launching atop proven rockets, this setup ditches complexity for reliability. Using throttleable, restartable engines fueled by nitrous oxide and ethane, propellants that laugh off cryogenic headaches. "We're closing the lunar cargo gap," Mueller proclaims in his blog, envisioning 2 missions yearly from 2028, dumping 6 tons of gear to kickstart infrastructure. mine helium-3, and spark an economic boom. The moon's weak gravity? A game-changer, slashing energy costs for orbiting exports compared to Earth's iron grip. Impulse's in-house mastery, from navigation algorithms to structural welds, mirrors SpaceX's vertical integration, but with a pragmatic twist, accelerating development as seen in the Mira spacecraft's 15-month sprint from blueprint to orbit. This isn't just competition, it's a philosophical showdown, questioning if Musk's all-or-nothing Starship gamble overlooks the moon's role as a safe harbor for testing the tech that could avert Martian disasters. Yet, the drama peaks with timelines that teeter on the edge of feasibility. Musk's casual springtime nod, hinting at 2026 for snatching the upper stage midair with tower chopsticks, sends pulses racing, promising aircraft-like reusability where rockets refuel and relaunch in hours. Flight 11's nail-biting hovers and precision banks over Mexican skies tease this future, navigating FAA-approved corridors that dodge cities like Monterey, hugging the Pacific and Baja, with harm odds slimmer than 1 in 10,000. But skeptics roar. Delays from heat shield woes, environmental snarls, and geopolitical friction could shatter this schedule. Airspace shutdowns disrupt airlines. And while Florida beckons with flexibility, Texas remains the crucible for orbital refueling trials, Artemis moonshots, and Mars odysseys. One misstep, a tile cascade, a guidance glitch, and the dream crumbles. As the curtain rises on this cosmic saga, the implications electrify. A space economy built on sustained outposts, resource bonanzas, and plummeting costs. Starship's reusability could unlock it all, but Impulse's lunar lifeline reminds us diversity fortifies. Will Musk's Mars mania prevail, or will moon pragmatism temper the blaze? Flight 11 doesn't just test metal, it probes our resolve, urging collaboration amid rivalry. In this interstellar chess game, every move counts toward a multi-planetary triumph or a cautionary tale of hubris. The stars await, but only the bold and the wise will claim them.